Starting with patient 2 loaded in the main GUI, we can go back to the process SPECT data sub GUI from the procedure menu. When we open that sub GUI, our previously loaded reconstruction will automatically load. This reconstruction is now associated with patient number 2, so that gets displayed, and our previously analyzed ROIs are still here in our ROI setup menu. So if you recall, for the left kidney, we have this segmented region that was segmented using the 40% threshold. But now I'd like to demonstrate segmentation of the left kidney in the tumor using the iterative adaptive thresholding technique. There's a reference to this technique in the description below this video. So that paper will provide details of this technique, and in this video I'll just demonstrate how this GUI can be used to actually perform this segmentation. So with the left kidney selected from this menu, and since we've already drawn this original ROI is the only needed first step to performing the iterative adaptive thresholding technique. Now, one thing we do need to set are some fit parameters, and if we go up into the tools menu under adaptive thresholding, fit parameters, there are different preset values. I will choose the one that corresponds to this particular camera, radionuclide, and reconstruction method. These are the values you will find for the clinical reconstruction method in the referenced paper. But keep in mind these fit parameters for performing this adaptive thresholding are institution specific, so these will need to be calculated using your own phantom experiment. So with these fit parameters in the adaptive thresholding panel, we can just go ahead and press the auto SBR button. So it will just go through and calculate the source to background ratio using only the ROI, this original ROI that we drew. Now we know it's finished when this plot shows up in the lower left window. This plot is just the source to background ratio as a function of the iteration number, where in each iteration the source to background ratio is getting updated. So the program's calculated the SBR to be about 10.6 for the left kidney, and at an SBR of 10.6 and with these fit parameters 37.3 plus 42.8 divided by the SBR, we get a threshold of 41.3%. And when you use a threshold of 41.3%, you get a volume of the left kidney of about 125 mils. So this is pretty close to the volume we were getting for the left kidney before, since we were applying a 40% threshold. But now that we've actually used the adaptive thresholding technique to get the volume, we can store this volume into our patient database. And notice that our dataset number has been set to 2, so when we store this volume, we're not overwriting any other information we've already stored into the patient database. Now, with the iterative adaptive thresholding technique, one of the features is that 2 different thresholds are used to segment each region of interest. One threshold is used, as in this case, to get an estimate of the true volume of the object, and a second threshold is used to get an estimate of the true activity, since in nuclear medicine images we do get some spillout of activity from this source region. We do need a lower threshold to actually recover or draw a region a larger region that recovers all of that spilled out activity. So since we've already calculated this SBR, we can actually accept this and just save steps we've done so far. And with this calculated SBR, we just need to hit the set threshold button, and this will calculate a new threshold to apply using these fit parameters for the true activity. This is the threshold now that we need to use to get an estimate of the true activity. So with this 10.3%, we do need to hit the retry segmentation. So this repeats the segmentation using a 10.3% threshold, and now we get an estimated activity inside the left kidney of about 41 megabecquerels. And if we want to save that into our patient database, we just need to make sure we refresh the database. This will put us at the next available dataset number, and we can press store. And we can move on and repeat the same steps in the tumor. So once again, we press the Auto SBR button. It just does some work going through iterations to get a final estimate of the SBR. So unlike traditional adaptive thresholding methods that use a manual technique to select background regions to come up with a source to background, a ratio of activity concentrations, this method does semi-automatically select the background region, only using that original information of that ROI surrounding the background and the source. So as we can see in the image, the tumor does have quite a bit more uptake than the left kidney, and we get an SBR of about 33. Now in this case, when an SBR of 33 is plugged into the true volume fit parameters, we get a threshold of 38.5%, and applying a 38.5% threshold, we get an estimated tumor volume of about 63 mils. Again, this is pretty close to the volume we were using already with our fixed 40% threshold, since this threshold is close to 40%. So we can go ahead and accept that segmented ROI. Accepting at this point will save this SBR that we've just calculated. And now we can store this new tumor data into the patient database. And the last thing we want to do is set the threshold for true activity. But actually first I would like to demonstrate looking at that segmented ROI again. For the tumor, we can see that definitely there is some activity outside of this region that's estimating the true volume of the tumor. So we're definitely losing some activity there in our estimate of the total activity. So let's see, we have a estimated activity of about 56.8 megabecquerels. When we apply the true activity threshold, so we set threshold in this true activity row, we get a threshold of 4.3% that's suggested that we use with an SBR this high, with an SBR of 33. So when we retry our segmentation using this 4.3%, we actually get an activity of 85.8 megabecquerels. So if we take a look at that segmented ROI, we see that indeed we do have an ROI that's now encompassing all of that activity inside the tumor. Just demonstrating the need for those two thresholds. One, to estimate the true volume, the second threshold to get this estimate of the true activity. So we can refresh our patient database and store. We also don't want to forget to save our progress in the process SPECT data sub-GUI. So again, this is test 2 where this patient's being saved. And now that that's saved, data saved, we're safe to close this sub-GUI. And back in the main GUI, again, we just do our usual loading of the patient to refresh and update all of the new data we've just acquired. Now with patient 2 loaded, if we go to the left kidney, we'll notice in the SPECT and other data panel, we have 3 data sets available, and we know that for activity, we used dataset number 3. Dataset number 3 is where we applied this THA threshold, or the threshold for an estimate of the true activity, and we used dataset number 2 to apply this threshold THV, which is the threshold to get an estimate of the true volume. So in this table, which summarizes the activity and volume of our left kidney, we can use 2 different thresholds to summarize each of those parameters. So for example, we have an activity of about 41 megabecquerels, which was attained using a threshold of 10.3%, and we have a volume of 125 mils, which was acquired using a threshold of about 41%. So this would be our SPECT data that we would actually want to use in the hybrid planar SPECT approach to get a proper time integrated activity coefficient. So we should perform the fit again, get this updated time integrated activity coefficient, which we can then save. And we can repeat this again with the tumor. So bring back the tumor. So right now, the main SPECT data set is set to the first data set for activity, the first data set for volume. If you look at that, that's a 40% threshold being used for activity, a 40% threshold being used for volume. We adjust that to the third data set for activity, the second data set for volume. Then we get our updated activity and volume. Actually, we should also set this as our main SPECT data sets for this region. If we press OK, that means every time we load the tumor, it will set the dataset number 3 for activity and volume, dataset number 2 as the default. We can perform the fit, calculate the time integrated activity coefficient, and we can store this data. Now, if I go back to the left kidney, I actually did not set activity set 3 and volume data set number 2 as the main SPECT data sets. So now in the tumor and the left kidney, we have these data sets properly saved. So that wraps up the use of the iterative adaptive thresholding technique for estimating an object's true volume and activity.